Why do some thoughts flash into our minds instantly, while others require grinding, deliberate effort? The answer might not lie in separate brain systems, but in the geometry of a single mathematical landscape. This paper explores that unification through a geometric theory of cognition. Current cognitive science faces a significant fragmentation problem. Researchers often treat perception, memory, and reasoning as if they reside in separate, incompatible boxes, lacking a shared mathematical language to explain how fast intuition and slow reasoning actually interact. To solve this, the researchers propose a unifying principle that replaces these separate boxes with a single continuous dynamic law. They define cognition as a Riemannian gradient flow, where the mind naturally moves in a direction that decreases cognitive potential. Let's dig deeper into the mathematical mechanics that make this unification possible. The theory rests on three core variables. First is the cognitive state, a vector representing internal configuration. Second is the potential, or energy, which combines accuracy and effort. And third is the Riemannian metric, which defines the geometry and determines the cost of mental changes. This geometry explains the classic psychological distinction between fast and slow thinking without needing two separate brain programs. Instead, the authors argue that the mental landscape is anisopric, or uneven. Steep slopes trigger fast, automatic reactions, while flat valleys force slow deliberation. This figure from the paper visualizes that specific geometric structure. You can see how the system rapidly falls onto a slow manifold, representing a habitual response, before drifting slowly along the valley floor as it engages in deliberation. The theory is mathematically elegant, but does it actually predict cognitive behavior? The authors provide a rigorous mathematical validation using Fenichel theory. They prove that this complex geometric system naturally simplifies into reduced slow dynamics, showing that the brain can operate efficiently without losing accuracy. In simulations, an agent choosing between two options successfully mimicked human hesitation. The fast, automatic variables aligned immediately, while the slow variables accumulated evidence until they reached a tipping point, replicating the phenomenon of sudden insight. Finally, this work has profound implications for artificial general intelligence. It suggests that AGI should not be built as a collection of hand-coded parts, but rather as a single geometric system where complexity, prediction, and logic are simply terms in the same potential function. To learn more, head to emergentmind.com.